Hi everyone, welcome to Mathemly. Welcome back to our neural network series. In our previous video, we looked at the challenges of training deep networks and how gradients, the signals that drive learning, can vanish or explode as they travel through many layers. Up until now, we have focused on data that exists in a single snapshot. When we predicted house prices, the network looked at the size, location, and age all at once to give us an answer. But the real world isn't always a still photo. Often, it's a movie. What happens when the order of your data is just as important as the data itself? Think about a sentence, a piece of music, or the fluctuating prices of the stock market. In these cases, you can't understand the now without remembering the before. Today, we are moving beyond static snapshots and diving into recurrent neural networks or RNNs and LSTMs. These are the architectures specifically designed to give neural networks a sense of time, order, and memory. Think about a standard feed-forward neural network. Up until now, the models we have built expect a fixed input size. A house, for example, has a set number of features like bedrooms, bathrooms, and square footage. But what about a sentence? Some sentences are 3 words long, others are 30. Standard networks don't know how to naturally handle inputs that constantly change in length. But the bigger issue is how they process that data. A standard network takes an input, processes it, and gives an output independently. It's like trying to understand a movie by looking at individual frames shuffled in a random order. You would completely lose the plot. Traditional networks struggle with sequential data, where the meaning depends entirely on the sequence and the order of events. For example, think about the phrases, "the dog bit the man" and "the man bit the dog." They use the exact same words, but the order changes the meaning entirely. This is where recurrent neural networks or RNNs step in to solve the problem. The word recurrent means occurring repeatedly. Unlike standard feed-forward networks that just push data straight through from input to output, RNNs have a built-in loop. Think about how you read a book. You don't wipe your brain clean before reading every new word. You carry your understanding of characters and the plot with you as you read each sentence. RNNs are designed to replicate this exact process. When an RNN processes a piece of information like the first word in a sentence, it doesn't just produce a standard output. It also calculates something called a hidden state. You can think of this hidden state as the network's internal short-term memory. It is essentially a mathematical summary of what the network has just seen. If we unroll that loop across time, you can really see how the magic happens. As the network moves through a sentence, it passes this hidden state forward from one time step to the next. So, when the network gets to the second word, it isn't just looking at the word in total isolation. It takes the current input and mathematically combines it with the hidden state passed down from the previous word. By constantly updating this memory at every single step, the network slowly builds an understanding of the whole sequence. Finally, it has enough historical context to make a smart, informed prediction. So, RNNs sound like the perfect solution, but in practice, they run into a fatal flaw. Remember our last video on the vanishing gradient problem, where the learning signal faded away as it traveled backwards through deep layers? Well, think about what happens when we unroll an RNN. Processing a sequence is exactly like training a deep neural network, just laid out sideways across time. If a paragraph is 50 words long, The network is effectively 50 layers deep. During backpropagation, the error signal has to travel all the way back from the 50th word to the first word, because it is repeatedly multiplied by small weights at every single time step. That learning signal shrinks exponentially. By the time it reaches the beginning of the sentence, it has shrunk to nearly zero. Let's look at an example. Imagine trying to predict the final word in this sentence. I grew up in France, I went to school there, I had a dog, and now I speak fluent. To correctly guess the word French, the network must remember the word France from the very beginning. But because the gradient vanishes during training, the network never learns to connect those two distant words. It might perfectly remember the last 2 or 3 words to ensure the grammar is correct, but it completely loses the context from the start of the sentence. It has a short-term memory, but it severely lacks a long-term one. To fix this short-term memory bottleneck, researchers created a much more sophisticated version of the RNN called the LSTM, which stands for Long Short-Term Memory Network. If a standard RNN is like a messy notepad where you just keep overwriting your notes until they become an unreadable blur, an LSTM is like a highly organized conveyor belt. The secret of the LSTM is a core component called the cell state. The cell state carries long-term information from the beginning of a sequence to the very end with almost no interference. But the network doesn't just blindly keep everything. LSTMs use special structures called gates, which are essentially mini neural networks inside the main network to carefully manage what goes on and off this conveyor belt. There are 3 main gates. The forget gate. This decides what information is no longer useful and should be thrown away. For example, if a story stops talking about John and introduces a new character Sarah, the forget gate learns to drop the memory of John so the network doesn't accidentally use the pronoun he later on. The input gate. This decides what new relevant information from the current step is worth adding to the cell state. In our example, it takes the new subject Sarah and stores her details safely on the conveyor belt. The output gate. This decides what specific part of that long-term memory needs to be pulled off the belt and used right now for the current prediction. This ability to successfully handle long-term dependencies absolutely changed the landscape of artificial intelligence. Before this, AI was mostly stuck looking at static pictures. But with LSTMs, neural networks became the backbone of sequence-based technology. Let's take a look at some examples. Speech recognition. When you talk to your phone, it doesn't just hear isolated sounds. If you say aloud, I want to write a right-handed character, the network needs context to know which version of right or right to use. LSTMs use the surrounding words to accurately piece together your voice commands. Translation. Translating a sentence isn't just swapping out words one for one. Different languages have completely different grammar rules. In some languages, the verb is pushed to the very end of the sentence. An LSTM can hold on to the subject in its memory for the entire sentence, ensuring the final translation makes grammatical sense. Time series forecasting. For predicting the stock market or the weather, the past directly influences the future. LSTMs can look at weeks or months of prior data, hold on to seasonal trends or patterns in their cell state, and use that historical context to accurately forecast what will happen tomorrow. Today, you hear a lot about transformers, the architecture powering large language models like ChatGPT. Transformers have mostly taken over because they can process entire sequences all at once rather than word by word. But understanding RNNs and LSTMs remain an essential rite of passage. They were the pioneers. They were the very first architectures that successfully taught machines how to remember. To sum up, traditional networks are great for snapshots, but RNNs are built for sequences. They use a hidden state to remember the past, but they struggle with vanishing gradients in long chains. LSTMs solve this by using gates to protect and maintain a long-term memory. In our next video, we are going to look at how neural networks see. We will explore convolutional neural networks or CNNs and how they revolutionized image recognition by mimicking the human visual cortex. If you found this video helpful, don't forget to like, share, and subscribe to Mathemly for more data science tutorials. Comment below with what you would like to learn next. Thank you for watching and see you next time.